Okay, question 3. Here it is. It's saying figure 3.1 shows the stress against strain graph for metal X up to its breaking point. So there's its breaking point there. We've got stress on the y-axis and strain on the x-axis. And let's move on to part 1, which says to use the figure to state the physical properties of this metal. And we're going to have to spell something correctly. So if we come back, what I would say is, if we look at this, well, we've just got a straight line, meaning that the stress is proportional to the strain all the way up to its breaking point, and that is indicative of a brittle material, which is the thing we have to spell correctly. And we should notice it's a 2-mark question, so we need a second property, and I would say is if we come back at it, well, it returns back to its origin, well, because it's stress compared to strain, so if we were to unload it before we get to the breaking point, it would come back and show 0 strain, so that would tell me that the material is elastic. Now if we come on to part 2, on the axes we've got to sketch a graph for a ductile material having a larger Young modulus value than the metal X up to its breaking point. So if we come back to the figure, what it's obviously trying to test you here, do you know what the Young modulus is on a stress strain graph? And that is the gradient of the line. So we're going to have to draw a straight line passing through the origin, and that's just not working very well, so I'm going to have to do it freehand. Let's come in here. You would obviously have to use a ruler. So a straight line passing through the origin with a steeper gradient, and we're going to have to show that it's ductile, so at some point there's going to be a limit to the proportionality, which is here, that's the elastic limit, and we're going to start showing the plastic behaviour of our ductile material like that. Now moving on to part B, we've got a stationary cable car. It tells us that the cable on both sides of the car is at an angle of 12 degrees to the horizontal. The radius of the cable is 2.6 times 10 to the minus 2 meters, and the stress in the cable is 1.8 times 10 to the 7 pascals, and it also gives us the Young modulus of the material of the cable is 2.0 times 10 to the 11 pascals. Okay, we don't need the diagram for this first part, so it's asking us to calculate the strain experienced by the cable. So what we need to look at here is, I know that the Young modulus is equal to the stress divided by the strain, and if I rearrange that, that will tell me what my strain is equal to the stress over the Young modulus. And we're given those things, so the stress in the cable is, also the strain is going to equal the stress, which is 1.8 times 10 to the 7 pascals, divided through by the Young modulus, which is 2.0 times 10 to the 11 pascals. Stick those numbers into your calculator, and to 2 significant figures we will come out with an answer of 9.0 times 10 to the power minus 5. And of course, because it's strain, it doesn't have a unit. Now if we move on to part 2, we now got to get the tension in the cable. And again, we can get that from the information in the blurb over here, because it tells us that the radius of the cable is 2.6 times 10 to the minus 2 meters, and we know that the stress, so we should know that the stress is equal to the force, in this case, which is going to be the tension T, divided through by the cross-sectional area. Now this has given us the radius, so the area is going to equal pi r squared, And if we rearrange this top equation and substitute this one in for t, substitute in for A but rearranging so t is the subject, that will tell us that the tension will equal the stress multiplied by the cross-sectional area, which is pi r squared, and substitute our values in. So 1.8 times 10 to the 7 pascals multiplied by pi, 3.14 will do, multiplied by the radius, which is 2.6 times 10 to the minus 2, and let's not forget that we need to square that, put that into the calculator, and that will come out at being 3.8 times 10 to the 4 newtons. And finally on to part 3, where we've got to work out the weight of the cable car. Sorry, I haven't that part of the question in, but it's there. So I'm just going to draw the weight of the cable car, which was here. Label that W, and we know that this is in equilibrium and it's a stationary thing, and from our previous answer we know that the tension is 3.8 times 10 to the 4 newtons, so we know we've got let's get to the pen, 3.8 times 10 to the 4 newtons pulling in that direction at an angle of 12 degrees, and we've also got 3.8 times 10 to the 4 newtons pulling at an angle of 12 degrees in that direction. Now I would draw that out as a free body diagram. So we've got our two tensions acting in that direction, and we add that one on, and if we add on the weight W, so that one's T, that's T, there's my weight W, they're going to end up back at the same point. And if I put that angle in there is at 12 degrees, then what I can see is obviously this entire triangle, because it's symmetrical, is isosceles, which means that this midpoint here will meet at right angles, and I know that that's 12 degrees. So if I use a little bit of trigonometry, which will tell me that if I just draw out the one triangle, so that's 3.8 times 10 to the 4, I've got an angle of 12 degrees, and this will be here, half of the weight. So half of the weight is opposite this here is opposite the angle I know, and the tension here is the hypotenuse. So opposites and hypotenuse tell me sine theta, so the opposite will equal is equal to the hypotenuse multiplied by the sine of the angle. And if I put those into the calculator, what will come out is that half of it is going to equal 0.8 times 10 to the 4 newtons. So when I double that, my weight will equal 1.6 times 10 to the 4 newtons.